Hey, welcome back to Fat Mama Physics! In this video, we're actually going to be doing some math today. Math. This series that I will be doing, it will be solely on the basics of algebra. So, definitely if you're doing Math 9, if you're taking Math 9 with me, this is applicable to you. So I decided at the very beginning of all my videos, well, not all my videos, but beginning of every section, hopefully, I want to just introduce a board game that I currently play, and I'll make it quick. So the first one I have here is code names. I chose code names also in relation to today's topic, but also just like a starter, since this is the first time I'm doing it. I decided to pick an easy game that everyone can pick up, and it's very fun. It's a great party game, great social game. It looks like this. It's rated pretty high. It's popular amongst families, friends, etc. What is the game about? So, essentially, this game is played between two teams, red and blue, and essentially what they want to do, it's kind of like Pictionary, it's kind of like Taboo, but what you get is, you get these nice looking cards, and they are laid out on a 4x5 grid. Ooh, math for you. And what's going to happen is that one person on every team has to be able to give out clues because they know exactly which cards on the table belong to their team. You can see that. So on this card, you can see there are some cards that are in red, some are in blue. It just means that every team has their own set of cards on the table that they have to be able to guess with the clue giver giving out one-word clues. Notice on this card, there's also a black symbol or a black card, and that card, it represents the assassin, meaning if a team accidentally guesses that card, that team automatically loses. The first team to be able to guess all of their cards on the table they win the game. So it's really fun. It's a lot of laughter. I love this game a lot. And why did I choose this game? Well, if you think about it, if you are the person doing all the guesswork, you don't know which one is the assassin. You also don't know which one of these cards belong to your team and what to guess. And that's the idea of a variable, is something that you don't know. And oftentimes in life we find that we are very uncomfortable with things that we're not certain of. We're human beings. By nature, we love to know things. We like to be certain. And once we face something we are uncertain, we often kind of withdraw. We become less comfortable. And this is oftentimes what I find with students when they do algebra, is there is a variable inside the equation and all of a sudden they shut down. And you're not alone in this, because I was also that student. And what happened was I did very poorly at the beginning of algebra, and it took a lot of practice and a lot of getting used to the fact that I just have to be okay with not knowing what that x is in that equation, what that y is in that equation, whatever that is. And also teaching the fact, or learning the fact, that I just have to be able to deal with everything that I know. I don't even think about what I don't know. I just leave it aside. I deal with everything I do know, and then eventually I will be able to know what I don't know. So it's just taking that patience, the time, the practice. It's kind of like something you kind of have to embody and learn as you're doing this particular unit. So I hope we can be able to do that as well. Okay, so my first lesson today is going to be an introduction to what is a variable, but it's one part of 4.1, which I labeled here, on inverse operations. So after I've talked about what is a variable, I will then go into things like, okay, what's an inverse operation, and of course going over examples. Without further ado, let's begin here. So I looked at a lot of the textbooks, I looked at a lot of the stuff, and personally, I hated algebra tiles. To me, they don't make sense, and it causes a lot of misinterpretations, misunderstandings, and misconceptions even. So I decided to model a little bit differently. Now, if you take a look at my arrow here, take a look at here. We work with polynomials. Maybe you have, maybe you haven't, but let's say you have, okay? In our class, we would have. We deal with variables such as x. And here I've just downloaded copied a few GIFs that I found off the internet in what I think what a variable is. To me, a variable is something that, as you look at it, you don't know what it is. It's changing over time until you know what it is. So here I have an arrow that is pulsing up and down, back and forward, and to me that represents a number line. So you have an arrow on a number line going like this, and what that means is you don't know what that number is on the number line. It can be very large number, it can be a very small number, it can be somewhere between. We don't know. So there's that. Some people might think of, okay, if it's a variable, maybe it's like a spinning die that never ends, or it doesn't fall, and you get a value, kind of like what's that ending scene in Inception where you have the spinning top and it just continues to keep spinning. So it's kind of like that same idea. It's got it's kind of like a spinning die. You don't know what it is yet until it stops. When does it stop? Okay, we get to that later. So here's a few models, and I hope you can see this. Now notice the computer might be a little bit laggy, but here's the idea. You have 3 of these little kind of spring-looking arrows. Imagine they are all springing out in sync at the same time But of course, my computer is not working. Anyways, the reason why is because here I have an expression. The expression here is 3x plus 7. And I'm going to model it. How am I going to model it? I'm going to model it with 3 of these x's. So imagine each of these springing arrows as 1x. Because I have 3 of them, I have 3 spinning, 3 pulsating number lines. And they're all pulsating at the same time. Meaning, if I decide one of them, all 3 of them will have exactly the same value. So they do represent the same number. We just don't know what that number is. So 3 of these pulsating number lines plus 7 little units altogether. That is, we've learned that before, hopefully. That's your polynomial, okay? 1 degree, of course, not many. But here is the idea. All of these arrows mean the same number. Here I have another set, another number, different color looking number line, pink, sure, okay? Notice they are pulsating at the same time. They're pulsating in sync. Maybe it's supposed to, it's just not doing it on my computer as a GIF. So here I have another example of 3y plus 7. It's the same idea, but now I have another variable. This other variable might be pulsating differently than my last variable, which is x. But all of my 3 y's should be in sync, meaning that they represent the same number. Okay. Now, if I'm going to keep scrolling down, then you might be thinking, well, hey, in polynomials, we didn't just deal with x and that's it. We had x to the power 2. We had x to the power 3. And you know what? I looked at the algebra tile model and I hated it so much. So here is my version. Here I have a polynomial with a degree of 2, x to the power 2 plus 7. So how can we represent this? Now, you have already seen it here, but this is kind of what I imagine it as. Since it's x squared, I have one pulsating line in this direction, and the other one should be pulsating in a second dimension, sort of like 2D, just like what the 2 exponent represents. And if you're thinking about square as the shape, yes, if you take the side length of a square and you square it, you get the area of the square. This is the same concept. But here, we don't know what this value is. So imagine if I can stop these arrows in time, like here, then that's how big my square is. If I stop it in time, say, when it's here, then it's a lot larger, okay? So it's something we don't know. And after we decided what the x is, imagine the area of it representing the value of that particular number. And of course, plus 7 units. I know it looks pretty cool, hopefully, if you believe so. But imagine what the third degree is going to look like. You're going to have 3 of these guys. Now you have a third dimension, kind of like 3D, like 3D glasses, yay. Okay, but I couldn't find a GIF to show that. Imagine you have a pulsating cube, and the cube's kind of like growing bigger, and then shrinking and then pulsating outwards again. And whenever you stop it in time, that's how big your cube is. And the volume of that, it will be represented by x to the power of 3, okay? So that's how I would like you to think of what a variable is. It's something you don't know, but once you set it, then you have a certain, that's kind of the representation I want you to see. Now, what happens, now before you've learned polynomials, you learn these expressions. In this particular unit, what we're going to be doing is we're going to be setting these particular expressions being equal to something else. Okay? So we're giving the whole expression a particular value, is what I'm saying. So here I have an example, 3x plus 7 equals to 10. Now once we have set a value, this variable x now can be determined. How can we determine it? If imagine I have 7 cubes over here, I have 10 over here. Now this is now we can actually talk about, imagine a scale. Both sides of the scale are equal. If I take too many things off of one side of the scale, the equation is no longer balanced. So whatever I do to one side of my equation, I have to do the same thing to the other side. So that's what I'm going to be doing right now with these units, these little tiny units. So what I'm going to do, and what I'm actually going to do, is I'm going to try to isolate these 3 little pulsating x's by taking away these 7 cubes over here. And because this is a scale, I have to be equal, fair to both sides of the scale. I will take 7 off the other side. If I do the same to both sides, even though they kind of go higher or down or whatever, they will be equal in weight. Okay, so I take 7 here, I take 1, 2, 3, 4, 5, 6, 7. I am left with these 3. Okay, I have 3 of those little tiny units left. Now I am left with 3 of these pulsating arrows, and then I'm just gonna do that to represent pulsating, whatever. That's gonna be equal to 3. Okay, or you can think of it, or if you like your algebra, then 3 of those arrows equals 3. So what does each arrow represent? You're right, each arrow represents exactly 1. Okay, so then by the time that we've set this equation here, the x's that are in the equation, we will have determined them already. They are set in value, and all we have to do is just go find it. Okay, that's all we have to do. We just have to go find it. It's like hide and seek. Ooh, where are you? Kind of thing. All right, and the same thing on this down here. Okay, so I also have x squared plus 7 equals 11, very similar to above. I'm going to take away 7 here, and this is 11 here. Okay, so I take away 7, 1, 2, 3, 4, 5, 6, 7. I am left with 4, okay? So I get this little cube-looking thing, sorry, my square-looking thing is equal to 4. Or, these 2 arrows. Another way you can think of it is x squared is equal to 4. And mathematically, you know that 2 squared, 2 times 2 is equal to 4. X is equal to 2. But it's not so much I'm trying to test your algebra skills. What I'm trying to show you is the fact that once we've equated this to something, then the x value is set in stone. Once it's set in stone, you just go and find it. And that's what we're going to be doing in this unit. And this is the reason why you don't have to be scared of variables, okay? We don't know it for now, but we will eventually know it. You just have to be patient, and you just have to put in the practice, okay? I hope you got something out of this video. Please stay tuned, because I am going to show you inverse operations and how to do some basic algebra. Thank you for watching. Fat Mama Physics signing out.